Thank you. Thank you for that great talk. Max, are there any live questions? I see there is a question on Slack. Chao Yi asks, um, from USTC asks, does the dark technique also work for RDMA-based applications? And currently dark is implemented in DPDK, and DPDK needs to dedicate or reserve some CPU cores and make cores at 100% utilization, right? Will dark affect the performance of the application itself when the workloads are high?
Thanks for the question. Actually, this is interesting. So for the first one, for RDMA, it depends on which mode you're working. So if you're working in the not one-sided operations and you're actually involving the CPU, it's going to be easier to implement dark just because you can do it in the CPU. I will step back for a second and say that dark is, you could implement it on the NIC, for example, or some other hardware. So it's abstracted away from its specific implementation. In fact, what we're discussing with Kostis and Jack is that it's likely that dark will be a good fit for Ghost or Syrup. And yeah, so for one-sided operations, if you could implement it on the network card, it could steer RDMA requests based on, for example, their size. There's a paper that's been doing sharding of key value stores based on the value sizes to avoid the head of line blocking problem for reading a lot of bytes versus reading a small amount of bytes. So you could use dark to do this kind of scheduling. Now the second question, so you're right, dark is implemented in DPDK. Yeah, so we do use a centralized model where we dedicate one core for pooling to serve requests, and that's where we implement dark. Dark is not going to impact the performance of the application when the workloads are high. In fact, it's made to improve the performance of the applications when the load is high. But maybe a more fundamental question we can ask is, can we get rid of having one core dedicated for polling, and what are the limitations of that? For the first question, it depends, in the sense that if you're really serious about single, like 1 or 2 microseconds latency, and you have like a network fabric that is very optimized, it's really hard to not process packets in a tight loop and do this scheduling decision in a tight loop without losing the centralized benefits for the scheduling. The second is, oh, shit, what I was saying for the second point. That's, I think, like we show essentially that if you care about utilization and you care about these short requests for the workloads we're targeting, you can actually run the machine at higher utilization with meeting SLOs than if you're using something like centralized load conferencing. I don't know if that answered the question. Sorry, it was a long answer.
Thanks, Max. Neil has a question. Neil?
Yeah, thanks. This is really impressive. I mean, 1 microsecond turnaround times are really difficult. So I'm curious about, I'm sure you must have had implementation challenges with trying to fit everything in the cache, because you miss L3, you take 100, 200 cycles hit. So I'm curious what takeaways you have for people who are thinking at the microsecond scale.
Well, there is definitely something that is super annoying, is that you arrive in a world where everything is a black box. You have to make a bunch of back of the envelope calculations saying, oh, if my packet size is about that and my L3 size is about that, and I'm receiving that amount of requests per second, how much concurrent buffers can I hold in my system so that they do fit L3? well, it's okay for some PhD student to spend a lot of time figuring these things out and being aware of these problems. But if you want to bring this kind of optimization to a larger set of application developers, it will be nice to have some way of, reducing the struggle of figuring those lower level hardware details. That I think that's one thing. In terms of, I also think that for this kind of microsecond scale workload, there is a lot of like hidden knowledge that everyone, like every panelist here knows about them. Like I'm sure Jack and Kostis knows everything about this kind of stuff. But you have to figure out that you cannot do any sort of dynamic memory allocation on this kind of path. So it means that your system has to bring on some sort of efficient memory allocator. Is that going to be available to everyone? Like what are the trade-offs in designing such tools? There is an entire ecosystem for the microsecond scale that is very niche right now and not really accessible to a wider range of programmers. So a lot of efforts we've seen at this years at SOSP, I think, are going into that direction. Like Irene works on the kernel and Syrup too. And I think those things are getting there, but it's a long way.
Thanks. And just one more question, tongue in cheek, like where does this end? It's a microsecond now. Is it going to be type of 1 second?
Gosh, I don't know if we have quantum computers. I think we're kind of hitting the limits in the sense that these applications are very niche. Like if you want to run at the microsecond scale, mostly either you're going to fetch a small amount of bytes from memory, or you're going to do a very specialized operation. I was mentioning machine learning workloads. If you just have to walk some branch in a decision tree, for example, that's fast enough. But for a lot of applications, it's not really a problem. The next thing where it could come to that is going to be, I think, disaggregated computing. When you need to do a lot of low-level resolutions of address translations, locations, like handling calls on a different node, and that might go to sub-microsecond, but then there is a more fundamental limit, which is the round trip time. I've been boasting about my single-digit microsecond stuff, but on my hardware, even when I plug two connected facts together, I have about 5 microseconds of transport between the two. So I'm sure this is going to get better, but can you also get the fabric to go from one rack to the other in less than a microsecond with the current hardware? I don't know.
Well, if I could interject, I would also say that there's a speed of light limit. So I do think that 1 microsecond is a really interesting abstraction because it's around 1,000 cycles where you can do something useful. But I think below 1 microsecond, you're really going to run into, it's too few cycles to be able to do anything useful. And the speed of light of stringing a cable across the data center, it's just not going to get below a certain amount. And so I think we are hitting the limit.
Yeah, that's a good point. Ludicrous speed.
Thanks, Max and Irene, for that. I have another question. I have a minute, so I can take that minute. Unless there's any other question here, I don't see any hands raised. So maybe I misunderstood, but a lot depends on how good your classifier is, right? In dark. So what is the cost of a mistake, and how do you ensure that it does a good job? Maybe I missed that detail.
So I'm glad you're asking the question, because we specifically for this conference, we added an experiment in the paper showing that multiple cases where misclassification can happen. So first, the dark is itself use a dynamic profiler, meaning that it's not asking you to provide a very like running time, an expected running time for your request. It's simply going to ask you for a way to distinguish between request types, so we can do the profiling and say, okay, this request type likely needs that amount of CPU cycles, etc., etc. Now, if the classifier is wrong, we also show in the paper that, for example, if you have a random classifier that picks, gets one request and just randomly assign it with a type, this is going to converge to centralized first come first serve. So in this case, which I cannot formally prove this is the worst case, but I think it's a reasonably adversarial case, the performance of the system cannot be worse than centralized first come first serve, which itself is already better than what you have in the data center today, which is decentralized first come first serve through RSS. Or actually, Neil and Tim can probably say better than me what's in the data center today.
That's right. But compared to a vanilla approach, you are losing out on throughput. So I guess that's the trade-off you make, right? You're always losing out on throughput.
So that is a trade-off that is unrelated to the performance of the classifier itself. We are willing to sacrifice some throughput for long requests so that we can guarantee good performance for the shorter request. It's a similar throughput that you have stuff like pFabric and other networking papers have been doing by using priority queues to guarantee performance for short RPCs and short flows in the data center. Yes, we do that trade-off on purpose. And one of the incentives to do that is we're going to lose throughput at very high load. So if you care about, there is a point past which the SLOs are going to be so bad that you don't really necessarily care about them. In fact, you probably want to run at a slightly lower utilization so that you can meet SLOs for both the shorter request and the longer request. So overall, we think this throughput, this trade-off is worthwhile. Yeah, I can talk about that for a long time, but maybe that answers the question already.
No, it does answer my question. Thank you so much. This has been great. I think we're out of time. Are there any other final questions or final comments that folks want to make? Great. So thank you all. I think we have a next session starting in 13 minutes or so. I'm not sure. So thanks again, and I hope you enjoyed this session as much as I did. Bye.
Thank you.
Thanks, everyone.